Okay, good. So let me just review very quickly what we have been doing so far. So I will do that by making a plot. I'm going to make a big plot. This would be time, okay, or temperature. Oh gosh, this is really confusing. So let me just put T or temperature. Now, as we said earlier, if you, I mean, just a quick review of what I've been saying. If I make a plot of the number density of some species divided by the total number density of baryons, right? Now let's just focus in on the neutrons, which is the thing that we've been discussing so far. So initially, like I said, neutrons and protons are in chemical equilibrium. So they start off with, at high temperatures, they start off with, very similar number densities. So here I'm drawing the case where we're looking at neutrons. And then at some point, at a temperature given roughly by, Q, which is roughly, 1 point, what was it? 1.2, was it? 1.3 MeV. Neutrons and protons remain in chemical equilibrium, and so the neutrons start to pick up a Boltzmann suppression that is proportional to E to the minus Q over T. But then it very quickly freezes out at some point that is roughly at T freeze out of 0.84 MeV. Okay? After this point, you would think that there would be processes that look like N plus P going to deuterium plus photons, but this is not effective because there are a lot of high energy photons out there, and so at this point, the neutron number density has decreased to something like 0.17, and then it will continue to decrease due to decays. And then we said that the deuterium bottleneck, which is where at some point we have few enough photons such that neutrons and protons can come together to form deuterium, ends at about 0.07 MeV. Okay, so this is the end of D bottleneck. And you can see that there's some decay happening within this amount of time. And then after that, the neutrons can all go into deuterium and higher elements. And so you'll start seeing a big fall off in the number density of free neutrons. Okay, so that's the picture so far. Any questions about this? Okay, so the key thing that we want to know is what is the final abundance here? Okay, at the end of the deuterium bottleneck, what is the number density of neutrons over number density of baryons? And the reason why this is interesting is because ultimately, if you think about at the end of the deuterium bottleneck, the neutrons can go into deuterium, right? But then it doesn't stop there. The deuterium can then go on and form, things like helium-3, tritium, and so on. But ultimately, if you look at all the light elements that can be formed during BBN, the one that's most stable, the one with the largest amount of binding energy per nucleon, turns out to be helium-4. So in fact, once the deuterium bottleneck ends, almost all neutrons get locked up in 4He because 4He is the most stable nucleus. of the light nuclei. Okay, so it's preferentially formed, and indeed almost all of the neutrons end up going into helium-4. So if we can figure out what this number is, then we immediately are able to figure out what the number density of helium-4 is. And that's our first theoretical prediction. Then we can do that, we can use that and compare against experimental data. Okay, so how do we do that? Well, we already did a calculation. We said it freezes out at roughly 0.17. This ratio freezes out at roughly 0.17. And then what we need to do is we need to figure out how much time elapses between TF and let's call this TD of 0.007. So how much time elapses between TF and TD. Okay, so this is quite a simple standard background cosmology calculation. We start from the definition of Hubble, which is A dot over A. And because we are in radiation domination, we know exactly what form this takes. This is going to look something like square root of A pi cubed over 90 G star to the half T squared over M Planck. Okay? This should look pretty familiar to you guys, but if you remember that 3h squared over 8 pi g is the total energy density, then you should see that this is somewhat familiar because energy density in the radiation domination scales as T to the 4, and now H scales as rho square root of rho, and so this scales as T squared, and then this just counts the total number of degrees of freedom. And in fact, we know this exactly after electron freeze out. So remember, electron freeze out happened at somewhere here, which is about 0.5111 MeV. And so after electron freeze out, we know that this should be roughly, well, after electron freeze out, it's exactly 3.36. But for most of this period, we can approximate this as 3.36. Okay? G star is sorry, let me write this properly. G star is approximately 3.36. Okay, well, after electron-positron annihilation is complete, we also know that, to a good approximation, T just scales as A inverse, right? Because there's nothing else that's going to freeze out in the EM sector to heat the electromagnetic sector. And so we can simply write this as, T naught squared A to the minus 2 over M Planck, where T naught is 2.725 kelvins, which is the temperature of the CMB today. Okay? All of this is a little bit approximate because the freeze out happens just slightly before E plus E minus freeze out, so it's a little bit annoying, but let's just put approximate signs here. Okay, that's great. We have A dot over A on the left-hand side. We have A to the minus 2 over on the right-hand side. Everything else is a constant, and so we can just do an integral, and we can define. Oops, I should go here. If we define A freeze out as T naught over T freeze out, or T, I said TF, sorry, AF is equal to T naught over TF, and then define A end of deuterium bottleneck AD is equal to T naught over TD, then you can just integrate this equation to get from A freeze out to A decoupling of dA, and I'm going to bring the A to the minus 2 over to the left-hand side and integrate, so that's just an A here. And so this is going to be approximately the integral of T of F to T of D dt of a bunch of constants. Over M Planck. Okay? So ultimately, you know, when the dust settles, you do the integral, you'll find that Td minus T freeze out is approximately half times 1 over Td squared minus 1 over Tf squared square root 90 over 8 pi cubed G star to the minus half and Planck. All right. And plug in the numbers. Everything's in natural units. Convert it to something that you are more familiar with. This turns out to be 270 seconds. Okay? So really all of BBN is kind of finished by order, you know, about a few hundred seconds or so. All right? What should you compare this to? Well, you need to compare this to the neutron lifetime, which I don't know if I wrote down the exact number, but from lab measurements, you know that Tn is roughly 880 seconds. Okay, so that's great. What this means is that between the freeze out of neutrons to the end of the deuterium bottleneck, there is some decay, but it's an order 1 amount. Okay, and so not all of the neutrons disappear, but this number is big enough that it's actually important to account for neutron decay. All right, so now let me just go back here and call this final temperature NN at the end of the deuterium bottleneck. And so therefore, NN at the end of deuterium bottleneck over N baryons is equal to what it was initially at freeze out, which was 0.17, right? And then now I need to take into account this decay. And so this ends up becoming a factor of exponential of something like 270 over 880. Obviously, everything here is approximate. What you want to do is you want to actually solve, you know, the Boltzmann equations between neutrons and protons at early times, and then also make sure that you are tracking deuterium bottleneck correctly, and so on. So everything you do it numerically. But you know, these parametrics are actually pretty good, and it turns out that this ends up being roughly 1 over 8. Okay, so at the end of the day, when the dust settles, the ratio, you have 1 neutron for every 7 protons for a total of 8 units. All right, so it's an order 1 number of baryons are actually neutrons. Okay, so the next thing I'll say is that since almost all neutrons go into helium-4, and you know, helium-4 contains 2 neutrons, and so I can also immediately get that N4He over N baryon at the end of BBN is just going to be roughly 1 over 8 divided by 2, which is 1/16. All right. This really is a perfectly good variable that really we should always talk about helium-4 abundance using this ratio. But unfortunately, historically, we have defined something called YP, and here I'm going to write YP of BBN, which we say is the mass fraction in helium-4. But really, for BBN, we always define this as just 4 times N4He over NB. And so this is roughly a quarter. Okay? And you need to pay special attention because whenever you'd use this in the context of CMB, when people say YP in the CMB context, they really do mean the mass fraction. And unfortunately, the mass of helium-4 is not actually 4 times the mass of just a proton, for example. It's actually 3.9 something. So there is a small difference between the two. And for example, when you use class, you need to be careful about this difference. It's a small difference, but conceptually they're actually different. Okay, that's just a brief remark. Okay, it's a wonderful prediction, and I mean it's pretty incredible. It's like it's one of these things where you're like, well, okay, it's like 15 minutes after the Big Bang, I can actually write down a tilde level calculation, get a value for YP that I can use to test this model of the Big Bang, right? And it's a combination of electroweak physics plus cosmology, and everything has to hang together. And surprisingly enough, it does. All right. So maybe I should go a little bit out of order and just give you what the experimental measurement is. So measurements of helium-4. Okay. What they do is they basically observe H2 regions, so ionized hydrogen regions, in very metal-poor galaxies. Which should therefore be dominated by, the primordial abundance. And essentially, you take spectra from these regions, and the spectra that you observe contains lines that correspond to absorption features for helium-4. And from the size, I'm not an expert on spectra, unfortunately, but from the width and the depth of these absorption spectra, you can infer what the abundance is for helium-4. And the current measurement that people kind of believe in, I guess, is that YPBBN is equal to 0.2453 plus minus 0.0034. Okay? So from observation, so this observed, all right, you get something that is basically a 1% precision measurement. Okay? So everything I've done here obviously is tilde level. What you want to do is you want to make sure that when you do this calculation, which involves electroweak physics, well, primarily it's just electroweak physics plus understanding when the deuterium freeze out ends, which really isn't that difficult because it's just the binding energy and comparing that with like number density of photons. You want to do that calculation also at the percent level accuracy, percent level precision, and it turns out that we can. So we can also get a percent level calculation, theoretical prediction for YP BBN to compare it with this. Okay, and of course that whole calculation really ultimately, yeah, is a test of everything that happens before 0.07 MeV. All right. Any questions at this point before I move on? Yeah. Uh-huh. Of hydrogen? I mean, so right. So this is a ratio of this to number density of baryons, right? So ultimately, it's a ratio of helium to hydrogen in these galaxies. So you do also have to measure the hydrogen abundance, but I think what they do is they just take a ratio of line strengths or something like that, essentially. Yeah. Absolute measurements of like the number density of hydrogen in these clouds. I think you can do it, but I'm not sure if they do it. Yeah. 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 Yeah, let me see if I wrote it down somewhere. Um, The thing is that it depends slightly on which value of omega b you use, as I'll say. So as you vary omega b, this changes a little bit. And so it really, like the theoretical prediction depends on what omega b you use. But at the Planck value, I think it's also something like 0.24 something. Yeah, so it's very good agreement. Definitely for this one, the agreement is very good down to this precision. Yeah, okay. Now, okay, so I've kind of stopped here and I said, well, okay, everything ultimately goes into helium-4. That's great. But then you also have other things. You also have deuterium, right? So let me make a plot here of helium-4 since I've already completed that discussion, which is that essentially helium-4 looks something like this. This is supposed to be green, but it's white. So let me just use dotted lines. Dotted lines. That's terrible. I'm sorry. This is helium-4. Okay. But then, of course, there's also deuterium, helium-3, lithium-7, blah, blah, blah. And so you also want to get all of those, right? So what do? Well, the key here is that now you have to deal with all of the nuclear reactions, right? So for helium, it's easy. It's just every neutron here basically just goes into helium. But then the rest of it, you need the details, right? So for example, you know that you have, in order to get predicting D, helium-3, and so on, how do you do that? Well, you know already that the first reaction of interest is this NP gamma D reaction, right? So that's the first thing. That's the first step. You get to you get from neutrons to protons to deuterium, and then you need to write down all of the reactions that get you from deuterium up to all of these other light elements. And you can imagine that there are a lot of reactions to go up to lithium, to go up to an accurate prediction of lithium-7, you need something like 60 reactions. Okay, and people have studied, not so much for lithium-7, they've not studied this that well, but people have looked at a whole bunch of reactions and figured out like this one is important and these other ones are not important, and so on, okay? But to go up to get deuterium and helium-4 right, you actually only need 12 reactions. Okay, which isn't so bad. But what you really need to do is you have to figure out what these 12 reactions are. And so for example, in order to, for example, let me just write down 3 reactions that are really important. And these are DP, so let me just write down important reactions. These are, DP helium-3, gamma, DN helium-3, and DD proton tritium. Okay, and the notation is just, it's these two things reacting to form these two things, and so on. Sorry, I wrote this wrongly. This should be like that. All right. Okay, so for these are 3 of the important reactions that you have to put in, and what you need to do is you need to write down, write down essentially Boltzmann equations of the form dN dt is equal to minus 3h nd, which is just the Hubble expansion. And then you need to write down, for each of these reactions, you will have something like nd np sigma v of dp to helium-3 gamma minus also, plus the backward reaction, which is N3HE times essentially N gamma times sigma V of 3He gamma 2dp, and then all of the reactions, okay? So you have a large network, you have basically, however many species you're tracking, which typically we track something like 7 or 8 species. You have to write down a set of differential equations with sigma v, okay? And so in order to get an accurate prediction, what do you need? You need the sigma v, which is a function of temperature, for 12 reactions, okay? All right, so that's the main input that goes into calculating and predicting the abundance of things like deuterium, helium-3, and so on. So the important one that people do very carefully is the deuterium abundance. And the deuterium abundance basically looks something like this. Okay, so this is the deuterium abundance. And the whole scale is all incorrect. Let me try to draw this again. So this is roughly 1/8. And really the peak is more like 10 to the minus 2. So something like 10 to the minus 2. Okay, so it reaches some peak at 10 to the minus 2 at the end of the deuterium bottleneck. And then after this point, you can form deuterium very easily, but then all of the deuterium then goes through all of these reactions that I've drawn here, and it goes to helium-3, and then ultimately it all goes into helium-4. Okay? And then what deuterium does is that it just falls off and freezes out, just as the usual freeze out in the usual freeze out scenario. All right? So again, in order to do this prediction, you need to get sigma v as a function of temperature for 12 reactions, compute this differential equation, and ultimately you will find that after a lot of work, you will find that this number here is roughly 2 times 10 to the minus 5. 2.5, sorry, 2.5 times 10 to the minus, well, okay, sorry. Let me say that again. This is roughly 2 times 10 to the minus 5. Okay? Okay? Now, it's important to note that in order to do this calculation, like I said, you need a sigma v, so you have 12 things that you need to add, at least 12 things. Really, you need to add all of the functions as a function of t. Then you need to know what the neutron decay lifetime is. And then the last thing that you need to know in order to do a calculation like this is the baryon abundance. And the reason why the baryon abundance is important is because if you look at these reactions here, right, when each of these terms, all of the n's here, they're all proportional to the baryon abundance, right? So if you have a higher baryon abundance, then each of these n's here have a slightly bigger number density with respect to photons. And so the number density, the energy density of baryons is secretly baked into this expression. Okay, so let me write that down. To get a BBN prediction for D, helium-4, these are the two that we have experimental measurements of that are very solid, or more solid than others. But you also can get predictions for the rest. You need a few things. One is the neutron decay lifetime. Tau n. 2 is sigma v as a function of t for at least 12 nuclear reactions. And the last thing that you need is little omega p. Okay? With all of these things, you can do a computation. All right, any questions at this point? Okay, so just to complete this picture, you can also have predictions for, you know, do I have other colors? I have purple. You can also have predictions for helium-3, which also ends up becoming something like 10 to the minus 5, roughly 10 to the minus 5. And then things like tritium, which is roughly 10 to the minus 7. And then also things like lithium-7, which is roughly 10 to the minus 10. Okay? So you can get all of these things. People have done these calculations up to like sodium, which is overkill, but you can do it. I'm not sure how accurate they are, to be honest, but people have done it. All right, any questions up to this point? Okay, so I've gone into a little bit of this, but now let me just go into more detail. I'm going to tell you how to use BBN as a test for ΛCDM cosmology. Okay, and I already alluded to the fact that we have a measurement of metal poor galaxies, H2 regions in metal poor galaxies, and that is something that we use to get YP BBN observed, which is 0.2453 plus minus 0.0034. And then again, you can also do something similar where you look for the line of sight along a quasar. You find a cloud with low metallicity again. So that's very pristine, so very low metallicity. And then you can measure the ratio of D over neutral hydrogen, regular hydrogen, which is just protons. And you find that you can get D over H observed to be 2.527 plus minus 0.030 times 10 to the minus 5. Okay, so this is also kind of at like the percent level precision. Okay, so what do you do? Well, since I need 3 things to get a BBN prediction, and this thing here is a ΛCDM parameter. Right? I can do this calculation marginalizing over the uncertainties of tau n and sigma v as a function of t. So I can calculate, for example, d over h as a function of omega b, marginalizing over uncertainties in tau n and sigma v as a function of t. Okay, so these, if you think in terms of how to do, MCMC and so on, these are the nuisance parameters that you want to marginalize over. You don't actually care about these, right? The thing that you care about is omega b. And so you can calculate d over h as a function of omega b, compare it with this number, and then that gives you a posterior on omega b. All right, does that make sense? Okay, let me comment a little bit about the reality of this, okay? It sounds straightforward, but really isn't. One thing that I will put to bed immediately is that if you're familiar with more of the particle physics side, you will know that there are anomalies associated with the neutron decay lifetime. So there are 2 main classes of experiments that people do where they try to measure the neutron decay lifetime and they don't really agree. And so there's some discrepancy to the decay lifetime. It turns out that discrepancy isn't large enough to be important given the precision of our both our theoretical and experimental uncertainties. So that's actually not a big deal. So knowing that this is roughly 880 point something is actually good enough to do the analysis. This one is the one that's more tricky, right? So how does this work? What you do is you look in the literature for people who have done nuclear physics experiments. So for example, there are people who have reported, shooting two deuterium particles together and trying to count the number of helium-3 that came out. And they do that as a function of energy. So that gives you the cross-section. And then you do a thermal average to get sigma V as a function of temperature. And then, but this is a function of temperature, right? So how do you capture the uncertainty associated with a function that varies as a function of t? That's actually really difficult. And people generally just say, let's just take the median value and have introduced one extra parameter that just kind of rescales the whole sigma v as a function of t up and down. Okay? But that's not quite what you want to do because it could really have tilts and stuff like that. But people worry about that, but they've not actually taken that into account. Okay? So there are a lot of things that are hidden in here. And also, how do you actually get this, right? You've got all these experimental data that have error bars and systematics and so on. You have to do some kind of fit. And then after you do the fit, you have to do a thermal averaging and so on. There are different ways to do this. And the final result, they don't quite agree with each other, as you'll see in a minute. Okay? But again, in principle, you can do this. You can find some way of parameterizing your uncertainties in tau n and in sigma v as a function of t, marginalize over them, and get a posterior in omega b. And the result is as follows. There are 3 different results, because there are 3 different groups looking into this. I mean, there are more groups than that, but there are 3 that are commonly considered, and they're up to date, and you can get their code and stuff like that. But they all report slightly different results. So we have 100 omega b is equal to 2.195 plus minus 0.021 from a group called Primat, and then 2.236 plus minus 0.034 from a group called Parthenope. All right? And the difference, like I said, has to do with how they treat this guy. Okay? So Primat generally uses more theoretical inputs to do their predictions for sigma v as a function of t, whereas Parthenope uses more just like fit a 4th degree polynomial. That's what you get, and then they do the computation. All right. This is to be compared with the CMB. As we learned today, the CMB also can be used to infer omega b. And so for the CMB, so this is BBN. For the CMB, you have 100 omega b is equal to 2.236 plus minus 0.015. This is Planck. And you're like, okay, that's great. But then it turns out that there's also some scatter on the CMB side. So 2.259 plus minus 0.017 from ACT, and 2.221 plus minus 0.020 from SPT. Okay? So everybody has a little bit of scatter. Everybody says that they're making predictions that are kind of percent level, or for CMB, it's even slightly better than percent level, but they all kind of agree. All right? That's the current status that we're at for BBN and ΛCDM. Okay, any questions about this? So one thing nice about BBN, omega b, you might wonder, like, well, why do I need this if I have the CMB? Well, one thing is that you can see that the precision is quite comparable, and we hope that in the future, like which element is driving this omega b inference? It's mostly deuterium, and currently, the way that we do the deuterium measurement, which is doing, looking along the lines of sites of various quasars and hoping to find very pristine clouds. Currently, we only have like 7 such clouds that we trust, and together we can get a kind of a 1% determination. But we hope that in the future, with future telescopes, we might be able to find more. And so this measurement can hopefully go down. And then also on the theory side, hopefully we can push this down as well, but that's much harder for various reasons that I can go into. But there is some hope that there will be a little bit of improvement here. And the second nice thing, of course, is that, if you want to do something that is independent of CMB, for example, if you want to infer H naught in a way that is independent of CMB, in that case, you would need omega B. And in order to avoid, if you want to do an independent estimate for H naught without using CMB data, you can use BBN to get omega B. And so you can do a BBN plus BAO combination to get H naught, for example. So that's something that BBN offers you. It kind of is a completely different set of systematics compared to CMB. Okay? Yeah. Comparable. Yeah. Yes. Yeah, it's roughly equal. Yeah. Okay. Yes. Yeah. So if you think about if you think about like the binding energy of hydrogen, right? So if I ask you what is the binding energy of hydrogen, this is equal to half alpha squared the reduced mass of proton and electron. Whereas for deuterium, obviously this is half alpha squared mu dE, and it's a tiny difference because mu is equal to me mp over me plus mp, and so it's mostly me, but this small difference is observable in spectroscopy. Okay. Any other questions? Okay. Another thing I want to mention before I move on is a little bit more about the sigma v as a function of t. These are the 3 kind of reactions that we really need to pin down in order to get deuterium. This reaction here, dp to helium-3 gamma, was measured in 2020 by the lunar experiment, and that really helped. Like it really improved our predictions by a lot. So that was really nice. But it turns out that this discrepancy between this Prima and Parthenopy is probably resolvable if we have also measurements of this and this, which we don't. Every time I meet a nuclear physicist, I ask if this is easy to do. It's funny, like this is done in Gran Sasso, and they announced this in 2020. But if you ask them, why don't you do this? It's because it's in Gran Sasso and there are a lot of like dark matter detectors around. And all of these reactions, like this one especially, will spit out a neutron. Well, if you collide 2 deuterium atoms, some number of the time it will emit neutrons, and then those neutrons will act as a background to the dark matter detector. So it's very hard to convince them to do DD collisions. They can do DP because this is what happens. You just get a photon, but DD is much harder. And so as far as I understand, these measurements are going to be much harder to get, which is unfortunate, but I'm hoping that will change at some point. Okay, if there are no questions, I will talk about BSM. Okay, any questions? Okay, so going beyond the standard model. The first thing I'm going to talk about is delta N effective, which we've already discussed. Okay, so what happens when you introduce extra relativistic degrees of freedom, right? So when you do this, since Hubble, Hubble squared is proportional to rho, inside rho here there is a rho standard model, and then now you have rho coming from this extra delta N effective that you put in. And so your Hubble is actually a little bit bigger than you expected. And so if you think about what happens here, right? The main thing that happens is that when does the neutron to proton interconversions freeze out? This point here freezes out when the reaction rate for things like any interconversion between neutron to proton, when this falls, or it's roughly given by Hubble. Okay, so if you increase Hubble, then the freeze out happens a little bit earlier, and because of that, the abundance that you get is a little bit more. Okay, so that's very easy to understand intuitively. For delta N effective more than 0, you will get an increase in the helium-4 abundance, or in other words, YP goes up. All right, and since you have a 1% prediction for, you have a 1% measurement of YP, you're relatively sensitive to delta N effective. Okay, that's very easy to understand. There's also another freeze out that I referred to earlier, which is the deuterium freeze out, right? And then this also gets affected. So both helium and deuterium get affected by an increase in delta N effective. All right. So you do the same procedure, right? You can get a BBN prediction with neutron decay lifetime, sigma v as function of t, omega b, and now you have delta N effective. So you have an extra parameter, and you can just do the whole thing, marginalize. Omega b and N effective will be your final 2D plane, everything else marginalized over. And the end result is that you get delta N effective of minus 0.09 plus minus 0.28. This is from Parthenopy, but really everybody agrees on this number. And the reason is because it's mostly just driven by YP. And YP is just driven by electroweak physics. And so there isn't this horrible sigma v of t that you really have to worry about. Okay, so everybody agrees on this number. One comment is that we let it go negative, right? Which actually really doesn't make sense, because you are thinking, we are thinking that we're introducing some new relativistic degree of freedom that is inert, and so this contribution to h squared should be positive. But for some reason, we always just, for simplicity, we just let it go negative, even though it doesn't really make sense. Okay, so this is just what is reported by everyone, which is kind of weird. Okay, this is to be compared with CMB. So CMB reports, so this is CMB, this is BBN. CMB reports N effective of 2.92 plus minus 0.18 for Planck, 2.73 plus minus 0.14 for ACT, and 3.17 plus 0.29 minus 0.33 for SPT 3G. All right. So a little bit of a spread here, but again, you can see that the BBN inference is not doing too badly compared to the CMB. And in fact, if you look at the Premart result, Premart generally reports smaller error bars. So that's another issue as well, like which error bars should we trust? But Premart usually reports smaller error bars, so I would say that the power of BBN compared to CMB at looking at N effective is comparable at the moment. If we ever build a new, well, actually Simon's observatory will already improve this significantly. Okay. What else do I want to say about this? I think that's it. Any questions? Yeah.
I guess this bounds apply if there is some effect before result. I was imagining something like there is some dark radiation or something which comes in thermal equilibrium between result and the end of the bottleneck.
Yeah, but if it comes into equilibrium, then you also change the rho nu or rho gamma. And then really you have to redo all these calculations, right? Because all these calculations assume standard model, well, not quite standard model, but you know what I mean? What I'm saying is that it's model dependent. Like if it comes into equilibrium, you have to ask like how does it come into equilibrium, and then put that into the calculation, and then that's yeah, that's right. Good. There's one more thing I want to mention, which is that yeah, it is comparable. Yes, CMB will improve a lot, but if you think about it, right, like this thing here is actually really not the same as this thing, because the N effective of CMB is the N effective during the period, you know, from you know kind of before recombination all the way up to recombination. So there's some you know redshift over which the CMB is sensitive to N effective, and that's kind of concentrated more towards recombination. Whereas this N effective that you're seeing here is really N effective during BBN, which is way before recombination. So really these two are different things and can be different things. Like you can write models where these are different. All right. So really it's you know, even though this will improve a lot, these are actually can be very different in realistic models. Okay. And then one more thing I want to say is that you can do CMB plus BBN. So you can combine everything. The real difficulty, I would say, is that, again, when you do the marginalization, right, if you're familiar with a CMB analysis, you know, you run class, you get a prediction for CLs, and then what you want to do is you want to compare with the Planck results. And Planck gives you some likelihood, and it gives you a set of nuisance parameters for you to marginalize over and so on, right? For BBN, you really should be doing the same thing, right? You should also be marginalizing over all of these in the joint analysis of CMB and BBN. And so in the tutorial that we will have, I think on Thursday, I will show you some recent effort from me and some collaborators to make this kind of joint analysis possible. Okay, like people have done joint analyses, but using some simplifications where you don't actually marginalize over this thing directly, but you can actually do it in a more principled way with more recent results. Okay. Okay. So any questions at this point? No, then I will talk about DM annihilation to E plus E minus. Okay, so again, you know, the way that I set this up was I presented you with two new physics scenarios that are quite generic. One is delta N effective, the other one is E plus E minus, and so these two will have an impact on BBN. And so I'll show you now how this can actually affect BBN and what we would see in terms of N effective. Okay? So let's imagine that we have some M chi that is much less than MEV. Well, it doesn't have to be much less, but maybe sort of less than MEV. Okay? Because you have this reaction, right? Now there's a when you think about going back to E plus E minus, sorry, let me start again. I'm going to talk about DM annihilation. So I'm gonna imagine that m chi is less than MEV for now, but then I'll come back and say that this also works for slightly more massive dark matter particles. So when m chi is less than MEV, it can't really annihilate to E plus E minus because E plus E minus is 0.5 MeV each, and so if chi is below 0.5 MeV, this annihilation can't happen. But you could, for example, go into 2 photons, which is definitely possible. Let's think about this simplified scenario for now, and then I will come back and talk about E plus E minus for heavier masses. Now, if you think about this, previously, in ΛCDM, we had, in the electromagnetic fluid, we had gamma, E plus, E minus, proton to and neutrons, and then this goes to photons, protons, and neutrons at T less than or equal to 0.511 MeV, right? But now, if chi's have this annihilation, and this annihilation cross section is relatively large, then what you get is that instead of just gamma E plus E minus, you also have chi. Okay, and I'm gonna do what am I gonna do here? Yeah, I'm gonna do self annihilation. Okay. Yeah. And so let me draw a plot of the temperature evolution of a big plot, A, T, of neutrinos and photons as a function of A. In ΛCDM, which I'm going to use white to draw it, we already saw that T nu scales as A to the minus 1, roughly. And then at something like 0.511 MeV, the photon temperature goes up a little bit because of the E plus E minus annihilation before settling down into something like that. Okay? Now, importantly, what I want to say is that this plot here, on this plot, we have one measurement, which is at A of 1. We know that the temperature of photons is 2.7 kelvins. Okay? This was measured by the FIRES instrument on board Kobe in the 90s, I think 1996. All right, so we measure the black body, we know that it's 2.7 kelvins. We have one data point here. Okay, now imagine you have this thing happening, right? So instead of having gamma E plus E minus only, you now have gamma E plus E minus, also chi, neutrons and protons, and then this goes to a final state of gammas, protons, neutrons, and electrons. Okay, of course there's a residual electrons. Let me rewrite this. Let me just write down only all the relativistic species. So relativistic. And so in the end, this just goes to gamma. And then here, there was gamma, E plus, E minus, and chi, and then this goes to gamma as well. Okay? So in this case, you would have two heating events, one at 0.511 MeV, and the other one at wherever m chi is. Okay? So you have two heating events, and so your curve should look something like, your photon curve should look something like one heating event, and then two heating events. But finally, because we have one data point here, right, the final temperature of the photons have to agree at 2.7 kelvins because that's what we know, that's what we measure. Okay, so this is ΛCDM. This is with chi with chi 2 photons, let's say. Okay? But what do you see here? Well, the first thing that you notice is that because I have an anchor point here at 2.7 kelvins, if I have two heating events, then the photon temperature had to have started at a lower value than we expected. Okay? We don't actually know what the photon temperature is here. We only know what it is here, right? And the second thing that you will see is that if I draw the neutrino temperature, which should look something like that, I drew it really badly. Let me try again. The second thing that you should observe is that when the neutrinos hit A equals 1, if you just draw this line, because there are two heating events, the final neutrino temperature is actually much lower than what you get in the conventional ΛCDM. Okay? So all I'm saying here is that T neutrino with chi to gamma gamma divided by T of gamma today, this is today, is going to be less than T of neutrino ΛCDM over T of gamma not today. Okay? Now this N effective, right, is proportional to T neutrino to the fourth. Okay? And so what this means is that with chi to photons, N effective goes less than 3. All right? So you'll see a lot of people, in a lot of papers, people say things like, N effective less than 3 is not well motivated or is less well motivated. It's actually pretty easy to get it to work out. Okay, all you have to do is just have some kind of additional energy injection at late times. Okay. Now going back to the caveat that I said that M chi must be less than MEV. It's also true that you will get this effect. For any M chi that is less than 10 MeV actually, right? So it's just a little bit more complicated because the chi's start to freeze out while neutrons are fully coupled. But then at the point where while neutrinos are fully coupled, but then at the point where neutrinos decouple, there's still a little bit of residual annihilation that will still heat the photons up a little bit compared to the neutrinos. Okay, and so actually you can be sensitive to dark matter masses up to about 10 MeV, and so you could actually be sensitive to processes like chi to E plus E minus. All right, it's just that I'm showing you kind of the simple scenario where all of the energy dump goes only into photons. All right, is that clear? So let's just do an estimate of this effect. So again, how do we estimate what this effect is? We go back to our good old friend conservation of entropy. Okay, and so we know by conservation of entropy that at neutrino decoupling, the entropy density is proportional to 2 from the photons. Well, it's proportional to T decoupling cubed, right? But I also know that the prefactor here is just going to be proportional to the number of degrees of freedom. There's 2 from photons plus 4 times 7 over 8 from electrons, so photons, E plus E minus. And then now you have an additional, you have an extra contribution from chi, which comes into equilibrium through reactions like chi to gamma gamma or chi to E plus E minus, right? And so it really depends on what G of chi is. It could be, if it's a boson with 1 spin degree of freedom, with no spin degrees of freedom, then that's just, what am I talking about? With 1 spin degree of freedom, that's just 1. But it could also have a bigger number over here. But let's just put 1 for now. Okay, and I can use entropy conservation again to say that 2 plus 4 times 7 over 8 plus 1 T decoupling cubed, A decoupling cubed, is going to be equal to 2 times T gamma naught cubed, A naught cubed at some other scale factor well after chi's have frozen out. Okay, and then I can use the usual relation between T decoupling cubed, A decoupling cubed to T to the neutrino temperature, which just redshifts as 1 over A after decoupling, to replace this, and then that cancels out A naught cube. And then this finally shows that I will get something like T naught cube is equal to, in this case, 4 over 13 T gamma cube instead of 4 over 11 previously. Okay? And so you can ask, what is the impact on N effective? Well, you know that N effective is proportional to T nu to the 4. And so N effective with chi is equal to N effective lambda CDM times 11 over 13 to the 4/3, which is 2.44. Okay? Did I erase N effective from CMB? No. Look at this and look at that. Okay? This is very detectable, extremely detectable. All right? So what this tells you is that the punchline from all of this is that any chi that is in thermal equilibrium with the EM sector with M chi less than or equal to an MEV is ruled out. Naively. Okay? And by naively, I mean maybe there's a very creative way to build a model that gets you out of this, but I'm not fully aware of whether this is really possible. To me, my feeling is that this argument is really quite hard to get out of. Okay, so people have suggested, people have suggested things like, for example, well, look, the N effective here is small, 2.44 is less than 3, but let's introduce, extra relativistic degrees of freedom. So a combination of the two new physics models that I just told you about to compensate for the low N effective. So let me add some new relativistic degrees of freedom that gives you an N effective of 0.6, so that everything ends up nicely at 3. Okay, you might think that works, and that works for the CMB, so that gets you out of the CMB limit, right? Because the CMB is only just sensitive to N effective itself. Okay, But this doesn't get you out of BBN. Okay? And the reason is that there is a difference between cooling the neutrinos and getting 2.44 and having this and then adding this extra relativistic degrees of freedom is different from having, let me say it again, having your neutrinos cold plus extra relativistic degree of freedom is not the same as standard model neutrinos for BBN, because BBN is sensitive to the actual temperature of neutrinos, because the neutrino, comes into all of the electroweak interactions that we're looking at. Okay, so that argument actually fails. So people, for a while people are like, this is fine. We can add extra relativistic degrees of freedom, get out of the CMB limit, but actually you don't actually get out of the BBN limit. And so this is quite robust. All right? I don't actually know how else you can get out of this. All right? Any questions about this? Okay, good. So in the last 15 minutes, I'm going to say a few words about CMB spectral distortions, because I think based on the votes, you're going to talk about lensing, right? Okay, so I'm going to say a few things about spectral distortions. Yeah, go on.
So what would happen if I go into equilibrium with neutrinos
Okay, if you go into equilibrium with all three at very early times, you're fine.
ratio is fixed, no?
The ratio is fixed. So you can come into equilibrium, but then the question is what happens when you freeze out? Yeah, so if you freeze out after decoupling, then you change the ratio, and then that's constrained. Yeah. Yeah. Okay. All right. So spectral distortions. Again, everything is going to be very kind of qualitative, just to give you a sense of how these things are important. Let's see, what should I erase? I'll erase this since I'm done with BBN. Okay, so spectral distortions. Okay, so we know that in ΛCDM cosmology, we expect photons to be in thermal equilibrium with electrons and protons. They scatter very rapidly, and so at early times, very very early times, you expect that photons are indeed in an equilibrium distribution. Okay, and not only that, at very early times, photons are able to undergo, not just Compton scattering, which is E gamma to E gamma, but also things like double Compton. So this is at very high temperatures, which is E gamma gamma to E gamma, for example, or the other way around. Okay. So what this reaction does is that if this reaction is efficient, you can consume and produce photons at will. And this means that the equilibrium distribution that you expect should be proportional to just 1 over e to the e over t minus 1. There's no chemical potential, mu is 0. Okay? So at very early times, you expect this. And then in the usual, in the usual picture, everything just stays in thermal equilibrium all the way till recombination. At recombination, it free streams. And as we learned, free streaming doesn't actually change the shape of this. And so in the end, we expect that we should observe something that goes as 1 over e to the e over t minus 1. Okay? And indeed, that's what we observed. So if you look at, as a function of frequency, if you measure the intensity, this was the Kobe virus result that I told you about in the 90s, where, we have a bunch of data points here, and the error bars are really, really tiny. If you actually, the error bars that I'm showing here, I mean, obviously I'm just sketching, but it really has been inflated by a big factor for you to be able to see it, even on this plot, okay? And it really is a black body, consistent with a black body at the level of 1 in 10 to the 4, okay? So you do a fit, you subtract out the best fit black body distribution, you find that the error bars, the error bars are basically at a level of 1 in 10 to the 4, okay, and it's consistent with the black body. And of course, the temperature is like 2.725 kelvins plus minus 0.00 something, okay? I'm sorry, I forgot what the actual measurement is, but it looks something like that. All right, it's an incredible triumph, because if you think about it, how do you actually end up with a black body, a perfect black body? Well, it really means that you have to be in thermal equilibrium at early times. And in terms of what cosmological model can do this, the expansion of the universe and the fact that the universe was initially very hot and dense means that photons can actually come into equilibrium with regular matter and then scatter and reach this equilibrium state. Is confirmed by this measurement. All right, so it really is like one of the key things that cornerstones of Big Bang cosmology. All right. Now, there are a lot of assumptions here. One is that there's double Compton initially. Once double Compton kind of stops, it just continues staying in thermal equilibrium with the electrons. They just stay in thermal equilibrium. And then there's a recombination, and then it free streams, and nothing else. Okay? Anything that breaks this picture, where you're not just scattering in thermal equilibrium, where you're not in like thermal equilibrium with electrons at the same temperature, will break this picture. And you will see, you possibly see some slight deviations in this spectrum. Okay? So let's think about what happens when we have energy injection or removal processes. Okay, so at very early times, I made the mistake of not actually writing down, let me see, I can probably call this up pretty quickly, so let me just do that. Right, okay. So let's think about energy injection or removal from some exotic source, okay? Now, if I do this at a redshift of z more than or equals to something like 2 times 10 to the 6, okay, at such high redshifts, you have double Compton, you have E gamma to E gamma gamma being very efficient. And obviously, if this is efficient, so is E gamma to E gamma. Okay? So imagine if you try to dump a bunch of energy into into the CMB, what will happen, right? So let's say you produce. There are many ways that you can do this. One way you can do it is you heat up the electrons, the baryons, relative to the CMB, and so now suddenly they're out of thermal equilibrium for a while, and then they're going to relax because they're going to scatter with each other and they're going to relax back into thermal equilibrium, right? The thing is that because you have these two processes, you can always, because these two processes are efficient, it's always going to relax after any injection. The spectrum will restore itself to a black body spectrum. Okay? Because these two reactions are able to bring you back into thermal equilibrium, and this reaction is able to change the photon number, which means that it's able to keep you at mu equals 0. The chemical potential is able to stay at 0. And so any energy injection at Z greater than 2 times 10 to the 6, you're not going to see it in the spectrum. The only thing that it does is it just changes the temperature by some amount, but you don't actually know what the temperature should be, right? Like if we knew that it should have been some number, then we would be able to see it, but we don't. The only thing that we know is that we have measured it and the number is 2.7 kelvins. Okay? So no distortion at this time. Okay? Now, once you go below a Z of 2 times 10 to the 6, and so the range, the exact range is something like 3 times 10 to the 5 less than or equal to Z of 2 times 10 to the 6. E gamma to E gamma gamma, which is the double Compton scattering, becomes inefficient. But E gamma to E gamma is efficient. Okay, so what does this mean? Well, you've lost the ability to change the photon number. So photon number is conserved now because the only scattering is just E gamma to E gamma. That doesn't get rid of photons at all. If this happens, you can still reach equilibrium because of this process. This process allows you to kind of shuffle the photons around, right? So you're able to reach equilibrium, but mu will now be not equal to 0. Okay? Because the photon number is conserved. And so imagine if let's say you were able to remove, just kidnap some of the photons, right? What's going to happen? Well, there's no process by which you can repopulate those photons. And so it's just going to go back to thermal equilibrium but pick up a chemical potential. Okay? And so we call this era the mu era. And essentially, any kind of energy injection, let's say you heat up the baryons relative to the photons, or you remove some of the photons, or you inject additional photons, whatever it is that you do in this part, you're going to pick up a chemical potential. And you're going to be able to tell this because the the distribution that you see is consistent with mu equals 0. All right? At even lower redshifts, so once Z is less than 3 times 10 to the minus 5, 3 times 10 to the 5, what's going to happen is that E gamma to E gamma just becomes inefficient as well. Now, when I say inefficient, I don't mean that the scattering drops below the Hubble rate, because that's when recombination happens, right? Which is not true. It just means that it's not able to redistribute photons quickly enough. Okay, so at this point, what happens is that essentially, if let's say you run into, you heat the baryons relative to the photons, all of the photons are kind of going to pass through these baryons, and they're going to get upscattered, they're going to get Compton scattered. And it's going to imprint some characteristic distortion that we call the Y distortion. Okay, there are a lot of details here that I'm not elaborating on, but you can show that in this period where essentially the photons are not able to reshuffle themselves efficiently enough, it will imprint something called the Y distortion, which is a characteristic distortion to the black body, and so that's why we call this period the Y era. Okay. So there are two characteristic periods at which, if you heat up the baryons relative to the photons, you get either a chemical potential or you get this characteristic Y distortion. Okay? So you can run through all of the different ways in which you can inject energy or remove energy and see if there's anything that can contribute to spectral distortion. So I have 2 minutes left, and I just want to roughly go through what are all the lambda CDM distortions. And then tell you very briefly what the new physics, what people use this for when it comes to new physics. In lambda CDM, well, you might say, well, shouldn't it just be a black body? Well, there are really tiny effects that come in more at like the 10 to the 6, 1 in 10 to the 6 level. One thing is that there are galaxy clusters and reionization, giving hot electrons. So these electrons are, have a temperature of roughly an eV, whereas the CMB is at more like 10 to the minus 4 eV today. And so when the CMB passes through regions where there are a lot of these hot electrons, there's going to be a Y distortion that's going to pick up. And so this gives you a Y distortion at the level of 1 in 10 to the 6. Okay, so that's nice. You can actually learn a little bit about reionization this way. Another thing that happens is heating from entry of small scale modes in the early universe. So these are well past the nonlinear scale, but they are coming into the horizon at very early times. And when these small scale perturbations enter, you can think about one perturbation being a little bit hotter and one other area being a little bit colder, and then they re-equilibrate. And so if they enter during the mu era, then you pick up a non-zero mu. And I think at the current expectation for the amount of power from the power spectrum in these small scale modes, you expect the distortion to be 1 in 10 to the 8. Okay, so very small. And then the last thing is recombination lines. So when recombination happens, the electron comes and recombines to a high N state in the hydrogen atom, and then it scatters down and it emits a whole bunch of line photons. And so on top of this, you should also see lines, atomic lines. And this is also at the level of 1 in 10 to the 8. Okay? So in terms of lambda CDM sources, it's like 10 to the 6, 10 to the 8, which is something that we think is achievable. So we really wanted to do this. I think we would definitely get this, and then this is probably a little bit of a stretch, but I think we're hoping to be able to do this. In terms of new physics, anything that injects energy or removes energy is in play. So for example, dark matter annihilation, dark matter decay, even dark matter scattering with electrons also can be probed, because dark matter scattering with electrons removes energies from electrons. Another thing that's really important is that there are many models in which photons can oscillate into other particles like axions or dark photons. In that case, you get some disappearances in the CMB, and then that you can also constrain using spectral distortions. I think I'll stop here. Yeah, thanks. Yeah. Yeah.
Well, it's a bit sci-fi, if you try to measure like the cosmic neutrino background, put a second dot on the temperature.
Yeah.
What would be like, what's the class of theories that you
So if you put another dot somewhere, I wouldn't really expect, well, it depends on how well you measure it, right? Essentially, if you're able to measure it extremely well, then assuming lambda CDM, you can actually determine n effect, like the n effective from neutrinos to a very small error bar, and then you can compare that with, you can see if that's consistent with n effective and CMB and BBN, and hope to learn about new physics there. That's the first thing that I can think of. Yeah, so it would really, right now we infer the neutrino temperature from n effective and assume that there's nothing else except neutrinos. But then with that, we'll be able to kind of disentangle, is it colder neutrinos or new physics? Yeah.
other comments or questions? Can I ask you about the new distortion?
Yeah.
Because I think even in things like Pixie,
Yes. Yeah. 10 to the 8, I think it's difficult, right? Yeah. Yeah, that's right. Yeah. But yeah, okay, another new physics thing that I forgot to mention is that there are many models where you have enhanced power at high K. And so, yeah, all of this gets tested by any spectral distortion. Yeah.
okay, no
Yeah.
other questions for Hongwan. Let's thank him again.
Thank you.